Our next speaker is Denis Grebenkov from École Polytechnique. The title of his talk is Rigorous Results on First-Class Time for Surface-Mediated Diffusion.
Okay, thank you very much. Good morning. So first of all, I'd like to thank the organizers for this beautiful conference. Today I will present results on some rigorous results on first passage times for surface-mediated diffusion. This is a result of a long project which was started around 2010 with Olivier Bénichou, Raphaël Voiturier and Pierre Levitz. Many results were obtained by PhD student Jean-François Ruprecht. And in the final stage, we collaborated with mathematicians from the University of Orléans that helped us to clean some physical uncertainties and allowed me to write the word rigorous in the title. So this is the outline of my talk. I will start with some basic motivation about why do we care about first passage times, what they are. I will present the results for the model of surface-mediated diffusion, present analytical solution for the mean first passage time, discuss the optimality of this intermittent model, and finally some conclusions and perspectives. And so all the papers related to this work, you can find them on my webpage. Well, the first passage or first exit or escape problems are very common in nature. You can observe them on a macroscopic scale when you have some animals which search for food or they try to escape through some holes. Of course, you have a lot of examples in microscopic level when you have chemical molecules which search for catalytic germs on a catalytic surface to start reactions. You have enzymes searching for specific DNA sites to start replication and many things like that. So there are very nice books and review papers. So in mathematical term, I would speak about kind of some bounded Euclidean domain. You have some active sites or binding sites or holes or something on the boundary, and then you have a particle which can move in this domain and it would search for the exit. And in this talk I'm not going to describe the specific escape problem which we are going to observe today. So let's me start with an example. So in my talk I will mainly illustrate the results for the disk, so the simplest domain you can imagine. At the end I will discuss some other cases for which the results can be obtained, but immediately I have to say that our goal was obtain analytical results. And the price to pay is that we have to do a lot of simplifications. So all the domains in particular, they should have some symmetries which would allow variable separations and things like that. So in particular the dynamics that I will consider, it's only diffusive dynamics here. So it's a very, very simple model if you think about biological applications. So you can think about first situation is surface diffusion. So when you have, well, in that case the domain it's a disk, the boundary is a circle, and you have a particle which moves on the circle with some diffusion coefficient d1, and then you have again a target or a hole of some size, angular size 2 epsilon or length 2r epsilon, r is the radius of the disk. And so we want to know the time needed to reach this exit. Of course, it's random time because it depends on the random realization of our stochastic process. And ideally, we would like to start to know the distribution of first passage times, or at least the mean first passage time. So what is the mean first passage time if we start from some fixed position characterized in that case by angle theta? So this is a very classical problem. So you have to solve the Poisson equation. So you have the Laplace operator, which in that case is particularly simple, just a simple derivative with respect to the angle. And so d1 Laplacian t1 equal -1. And of course you have to impose boundary condition. So to say what happens when a particle arrives on the target. And here if we assume that we are interested for the first arrival on the target, we impose what's called Dirichlet boundary condition, so the t of 1 is 0 here. And that's very natural because if theta is the starting angle, so if you start on the target, you immediately, it's already done, so the exit time is 0. Okay, so this is very easy problem to solve. It's essentially one-dimensional problem, and you have a quadratic solution of this problem. And in some cases, you don't really know what is the starting position, and so it's convenient to average over the starting point. So in this talk, I will often describe, and most of the results will be presented for the global mean first passage time when we average over uniformly static initial position. So you compute this integral. Again, for this case, it's trivial, and you get this result. So that's classical. So here there is nothing interesting in this case. So let's go to the bulk diffusion. Again, the same problem. You have a domain, you have a boundary which is impermeable for the particle, you have an exit or a target, and again you want to know what is the mean first passage time if you started at some fixed position characterized by radius r and angle theta. So again, the mathematics is essentially the same. You have to again to solve the Poisson equation. In that case, the Laplace operator is a little bit more difficult. You have to write it in polar coordinates. You have to impose, as previously, the Dirichlet boundary condition on the target. So when you come to the target, it's 0. But else we have to say what happens on the boundary. And so if we assume that it's impermeable, particle cannot escape across the boundary, so we impose what's called Neumann boundary condition. It looks very similar, but it's much more complicated in mathematical terms because you have a mixed boundary condition. So on the same surface, you mix Dirichlet and Neumann conditions. Well, this problem was analytically solved by David Hoffman and his co-workers in 2006, and there is a very nice review about all this related stuff appeared quite recently. So I'm not going to present how the solution works. I'll just give the result for the global time average. So when we average over all starting positions uniformly distributed in the domain, and so you get this expression. And there is a conceptual, very important difference between two cases. In the case of surface diffusion, well, essentially it's one-dimensional diffusion, so you cannot miss the target. And so if you take the target point-like, so epsilon equal to 0, you can have still a finite limit. In this case, when you go from the bulk and you diffuse in the bulk, then if the target is very small, it becomes more and more difficult to find the target, and so this time logarithmically diverges when epsilon goes to 0. Okay, so these are different cases. Again, you have these papers, books, and reviews which describe this first exit problems, first passage time problems. What was our motivation? In fact, in practice, in real systems, often you don't have either surface diffusion or bulk diffusion, but have a mixture of two of them. Because if you think about a particle which moves in a bulk, when it approaches to the surface, when typically you have an interaction, local weak attraction between a particle, it can be water molecules, so it can be some proteins, with the surface. It can be specific or non-specific, so there are all kinds of situations. But often what you expect is that a particle diffuses in the bulk, and then when it comes to the surface, it can be adsorbed for some time. And this is an adsorption state. It can either be fixed, or it can also move on the surface. It can move just by hopping on the surface, or it can move in some surface layer near the surface. Again, there are different chemistry, different biology, different physics, can be microscopic physics can be inside, but you often have a situation when you have a mixture of surface and bulk diffusion. And that was essentially our motivation to study what do we get. And this is why we introduced this surface-mediated diffusion, so a very simple model which tries to mix these two situations. So again, you have a domain, you have a target, you have a particle, and it starts somewhere, well, for instance, in the bulk, then it diffuses until it hits the surface, and then once it hits the surface, it can be adsorbed on the surface, and it can move with another diffusion coefficient d1 on the surface for some random time, and then it is desorbed from the surface. So it's rejected to some small distance a You can think about A is a rather technical parameter, but you can think about it as a width of the surface layer. And then it starts to diffuse again. It can be reabsorbed, and in this manner it moves, and finally, some way, it finds the target. And also, you can consider that it starts from the surface, and again, it can move and can be disturbed, and finally, it can reach the target from the bulk. So in this model, you have essentially two states. So you have intermittent process between surface diffusion and bulk diffusion, and from the bulk diffusion to surface diffusion, it's just hitting. So when a particle hits the boundary, it is absorbed. And from the surface diffusion to bulk diffusion, it's the desorption process. So you have to characterize how long a particle stays on the surface. And well, within this model, we use just exponential random distribution of times, which are characterized by the desorption rate lambda here. So let me show here. So yeah, so we use this law, and lambda is the desorption rate. So you can think about 1 over lambda. It's the mean time that the particle stays on the surface during the surface diffusion. Okay, so now we have a simple model which has just several parameters. So surface diffusion coefficient, bulk diffusion coefficient, well, the size of the domain, the size of the target, ejection distance, and desorption rate. So how can we solve this problem? So we introduce two mean first passage times. One if we start from the surface, and another one if we start from the bulk. And then we have to rewrite these equations. So essentially, let's start with the first one. So for the surface diffusion, so we have a diffusion mechanism, and then we have to include the desorption process. So, and since we assumed the very simple exponential law for the lifetime on the surface, then in fact it's equivalent to the first order kinetics. And so this equation can be easily modified. So you just add a linear term which involves two concentrations. So the boundary condition is not modified here. And then of course we have to, the bulk diffusion doesn't change because we don't change anything in the bulk. The boundary condition on the target again doesn't change. What we have changed this condition. Before we said that for bulk diffusion it was just purely fully impermeable boundary. Now we have to include the adsorption on the boundary. And that's a quite natural thing to do. It's just to ensure the continuity of these two densities. So if you start from the bulk but the starting point approach to the surface, then the two densities, two mean first passage times should be equal. So we have this coupled system of coupled partial differential equations that have to be solved. And what you can do in principle, so you can see that you have two equations, and this equation in the bulk, it's determined by the boundary condition here. And so formally you can write the solution of this equation as an integral operator, and you can substitute it here. And so in that case you can just get some integral differential equation on T1 of theta. So you can, in this way, you can remove this T2 part, but you have to deal with integral differential equation. So all this presentation, right up to now, it was general. In fact, well, I described it for the disk, but you can do it for any domain, well, relatively smooth domain. So in fact, you just need to use the appropriate Laplacians. You have to use normal direction to make reflections, but the formalism is quite general. From now, I will really use the simplicity of the domain to solve the problem. Again, my goal here is to present some analytical solutions. So, what can we do? In fact, well, we can search for the solutions in some standard forms. So T1, it's a function on a circle, so you can decompose it in Fourier series. Because of the symmetry, we don't include sign terms. And for T2, we put a general solution which satisfies this equation with the same coefficients an as here. So in this way, we need to solve the problem for the coefficients. And again, even if you try to solve this problem for the bulk diffusion, you know that that's the most difficult part. So how to get expressions for the coefficients. And to save time, I don't, because it's really technical and I'd say rather boring, I would say then you have a miracle which happens, which allows you to solve this problem. The details you can find here in these papers. And the solution is the following. Okay? So, well, it's a rather long expression, but it's not so complicated, so let me remind what you have here. So it's a global mean first passage time if you start from the surface. You have the radius of the domain, surface diffusion coefficient, A is the rejection distance, D2 is the bulk diffusion coefficient, epsilon is the angular size of the opening. So that was the model, so the parameters of our model. But you also have two more ingredients, psi n and lambda n. So these are some parameters for which we have again explicit formulas. So while I'm not going to describe in details, but these are some spectral parameters. So lambda n are some eigenvalues of an operator, and psi n are the projections of eigenfunctions of this operator onto some other functions. Yeah, you can find details if you want. What is important here that these parameters, they only depend on epsilon and a. They do not depend on all other parameters of the model. And that allows us to study how this time would, for instance, depend on the desorption rate. And that's what I will show you. Just to give you an example, not to leave you with the feeling that I'm cheating here, that, well, for instance, if you take a very simple case of epsilon equals 0, you have very explicit formulas for these parameters. And in that case, you have really explicit solution for this problem. You have nothing hidden here. You can use it very easily. Well, you can easily compute this time, even for this case. But of course, the main purpose, again, is not for computation, because for computation, you can just solve the original problem by finite element methods. It's quite easy. But is to study analytical properties. Okay, so let's focus on the properties. Well, first, it's interesting to see what are the limiting cases. So when we take lambda equal to 0, so it means that the mean time which particle stays on the surface is infinite, so you recover the surface diffusion. That's natural. And if you take the general solution, take lambda equals 0, well, naturally you recover the solution I showed you before just for surface diffusion. The other case of bulk diffusion corresponds to the limit lambda goes to infinity. In fact, lambda goes to infinity, it means that once a particle hits the boundary, it stays on the boundary infinitely short time, and then it's reflected back. And so it corresponds to the bulk diffusion. Well, unfortunately, and quite expectedly, this limit is not so easy to deal as in that case. Well, formally you can see that lambda is here, and lambda is here. So if you take formally lambda goes to infinity, you can say that you have some constant here, and it would diverge. It's not true, because then you have to deal with the behavior of this series, which is has singularity. Well, there are stuff to do. Oh, I'm sorry. But it can be done. In particular, well, we retrieve the asymptotic results obtained by David in this limit. So in that sense, it's consistent. So we retrieve two limiting situations. But now we can study, of course, the most interesting part is to study the transition and what happens in between. So here I would plot the mean first passage time as a function of desorption rate, other parameters fixed. And here you would have, well, you have this expression gives you the point here. This expression gives you some limit when lambda goes to infinity, and then we have something in between. So let's first consider the situation when the surface diffusion is more efficient. So when the mean first passage time is smaller for surface diffusion than for bulk diffusion. Well, in principle, as you can see, you have different parameters d1 and d2 which control how fast the surge would be, and so you can consider different situations. Well, here you have three options. Well, first you have an option when just mean first passage time monotonously increases when lambda goes to infinity. What does it mean? It means that the surface diffusion is the optimal surge process. So the best you can do, you can hit You can arrive onto the surface, and then you stay on the surface. But you also may have another situation if it starts to decrease, and then it catches the limit. And here there is something which is quite interesting from my point of view, because this result, it shows that the intermittent behavior, so when you switch between two modes, it would be beneficial for search. So you can reduce the mean first passage time. So you can find a target, or you can start the reaction faster than in two cases. And why it's counterintuitive? Because you have two modes of motion. You have surface diffusion and bulk diffusion. And clearly, with this condition, we say that the surface diffusion is faster. So naturally, if you say that you have a fast process and a slow process, if you would mix two together, well, you would lose efficiency. And here, it's not the case. And so, well, how you can decide between these two situations? Well, in fact, it's just enough to consider the derivative of this time with respect to lambda at 0. And if the derivative is positive, then it grows. If the derivative is negative, it decays. So this is a sufficient condition for getting the intermittence efficient. And since we have an analytical formula for T1, we can take the derivative. And what we obtain a threshold for the ratio between bulk diffusion coefficient and surface diffusion coefficient. And this threshold depends, again, we have explicit formula, on epsilon and A. And so if bulk diffusion is fast enough, then the intermittence is efficient. If bulk diffusion is not fast enough, well, in that case, surface diffusion is efficient. But what, yes?
Why doesn't A scale out with the radius? I mean, I would have thought that if you rescaled everything by the radius...
well, A is the length, which you can measure in terms of the radius, but it's still a parameter.
Yeah.
In fact, well, maybe your question, well, why do we need this A at all? So can we take A equal to 0? Well, we will take it to 0, for instance, just here. I will say that if you take, I'll just finish this. So what was quite counterintuitive, that if you take just, well, the limit A equal to 0, epsilon equal to 0, the threshold is below than 1. I would expect that, for instance, if you had a threshold like 10, that would be natural. So if your bulk diffusion is 10 times faster than the surface diffusion, well, do bulk diffusion. If it would be comparable at least to 1, okay, that would be still reasonable. But here you have a threshold which is smaller than 1. So in fact, you have a motion, bulk diffusion, which is slower by itself, so the mean first passage time is higher, and the bulk diffusion is slower than the surface diffusion, but still it can be beneficial. Well, of course, in practice, surface diffusion is slower than bulk diffusion. So, and just to come back to this parameter A, in fact, if you consider the original definition, if you don't use A, or if you say A equals 0, it means that when you reject it, you immediately you still stay on the boundary, and you will be reabsorbed immediately. So you need it's a kind of regularization parameter that you use. But again, physically, it means that the width of the surface layer where you have the attractive interaction to the boundary. Okay, so I emphasize that this is sufficient condition because, in fact, what you also have the third option. It's like here. So, for instance, you start here, and then you decrease, and then you increase again. Well, we never observed this in practice, but we couldn't prove mathematically that it never happens. So, it's, if you like, it's open problem from a mathematical point of view. Physically, well, we didn't see it in any situation. Or other situation when you have some oscillation, many oscillations like that. So, sorry?
The y-axis is averaged over all initial positions in the bulk. Sorry?
This one is average over all initial positions on the surface, because T1 is if you start from the surface.
Oh, right.
But in fact, well, all the solution is obtained for T2 as well. They are related. And in fact, you also have solution local, so for each, if you fix a starting point. But so with this method, you can obtain the complete solution in general. But just, well, I think this one is more representative to some extent. It's already averaged. So, because otherwise, you have too many parameters to show. Okay, so we never observed it, but again, it's couldn't be excluded mathematically at least. So what I presented before, it was just schematical story. So now our numerical results. So, well, numerical, I mean, we implemented these formulas, and I just took some values. So here is, well, the scales are R equal 1 and D1 equal 1. So fix the length and time scales. So first we start with the point-like target. We have two bulk diffusion coefficients, one which is smaller than the threshold, the second one is larger than the threshold. Well, A is small here, as usual. And again, so here are the results. So here it's a limit, theoretical limit. And then for the first case, so what theory predicts that it should be monotonic increase. That's what we observe. And for the second case, there is a decay and then an increase. Well, in this particular case of a point-like target, you don't have a plateau here because mean first passage time by bulk diffusion diverges, and we obtain the asymptotic behavior. Well, we show that it's square root of lambda. And then, well, results are very similar if you take just small target. So here, again, now just you approach some limits, but the same features about the optimality. And finally, if you take very large target, I emphasize that our approach is not limited to narrow targets. So you can use any size of the target. So for instance, epsilon here it's 1, and the size of the target is 2 epsilon, so in fact it's like 1/3 of the whole surface. But in that case, you can see, so for the first case, d2 equal 1/2, still the bulk diffusion is not efficient, and you have monotonous increase. But in the second case, the bulk diffusion becomes more efficient, and so you have here monotonous decrease. So in fact, if you don't have the condition that the bulk diffusion is large, the time for bulk diffusion is larger than for surface diffusion, then we showed again, and it was not obvious, that we always have a monotonous decrease. So in this situation, you cannot have an optimum, because the optimum would be just always use the bulk diffusion. Okay, so this was illustration for the disk. Of course, well, you can extend this technique, and when I say you can, it was done, so you can find these results. So you can look sphere, you can look annulus either on a plane, or you can look have some spherical shell. You can use some rectangles or parallelepipeds. You can use tors. So I mean, you can, in fact, you can think about any domain in which you can separate variables and use this technique. So, well, for two-dimensional case of the disk, you can also consider multiple targets. Well, in that case, the trick is that the problem is reduced to diffusion in sector, for which, again, you can solve the problem analytically, and so you can consider multiple identical targets. It's possible to introduce the radial forces. So what I presented it was just for the Laplacian operator, but you can also introduce radial forces. The expressions became more larger, but the results are quite similar. And these radial forces, for instance, if you think about very simple model of a cell, which you would model by sphere or by spherical shell between the nucleus and the membrane, and these forces can mimic, in a very rough approximation, some active transport, so some drift by motor proteins, and you can look on the effects. Well, you can also include the partial adsorption, so if a particle arrives onto the boundary, then maybe it's not adsorbed immediately, but it has some fine probability to be adsorbed or rejected, and then again you modify these conditions and you can write again the results. So all this was done, and there is also another extension which is maybe more general. So we worked on an extension, so we also obtained the results for the first passage time probability distribution. So in fact, in that case, essentially you need to move from the Laplace, from the Poisson equation, well, from the inhomogeneous Laplace equation to inhomogeneous Helmholtz equation. Well, it sounds like very simple, but in fact, well, conceptually it is. So it's not much complicated, but technically it's really much complicated. So in fact, what was done here, we only considered the bulk diffusion here. So we didn't extend the results for the distribution for the surface-mediated diffusion. I think it's feasible, so I do not see any reason why it shouldn't work, but it just the computations are technically involved. And there is another problem which only about splitting probabilities, which first appears to be unrelated. So what is the problem? So now you have two targets, and you want to know what is the probability that the particle hits the first target before hitting the second one. So for instance, you can think about animal, which needs what the probability it finds the food before it is trapped or by hunted, or you can think about some protein and think what the probability that it starts some reaction before it exits the domain, or things like that. And so in fact you can show that this splitting probability can be expressed in terms of the mean first passage times, and then you can use all the results. Okay, so just conclusions. So we proposed the analytical solution for the mean first passage time of surface-mediated diffusion in a rather general model. Well, again, it remains very simplistic. I emphasize again that we include large targets, so it's not a narrow escape limit. And I think what is the most interesting is that we show that intermittence can be beneficial for such process, so it can reduce the mean first passage time. And of course, well, this idea to some extent is not new in the sense that this facilitated diffusion mechanism was proposed in the 80s to explain the observation in biochemistry. But here it's a kind of analytical model which allows you to play with this problem and to see how different parameters enter in this problem. So, and well, there are of course, as usual, many perspectives. Well, first, and that's a practical question, how large the reduction of the mean first passage time can be? So how large the gain can be done with this intermittent process? Because you can think about the following. So for instance, in chemical applications, you have catalytic, you have catalysis, catalytic surface on which you have some catalytic grains, and a particle has to diffuse or move to these catalytic grains, and when they find it, then it can initiate the reaction. In many practical situations, the catalytic grains are very expensive. It can be platinum, palladium, or things like that. So you have really care about to reduce the number. And the question would be, if it's possible, if surface, well, in that case you have only bulk diffusion, but if you would have surface diffusion, would it possible to make some coating of your surface and to make a particle be attracted, absorbed on the surface, and then induce this kind of surface-mediated diffusion? And in that case, you can try to play around if what is the best coating to use, what is the desorption rate to ensure, and things like that. And to do that, of course, well, making this coating is expensive as well, and so the question how much you can gain. And if you are in two-dimensional case, the answer is simple. So if you consider the limit epsilon goes to 0, so the size of the target is very small, then you can gain as much as you like. So in that case, you don't have a limitation. You can make a gain arbitrary. And the reason is simple because, in fact, for the surface diffusion situation, the constant is the mean first passage time is fixed. It's a fixed limit. For bulk diffusion, it's infinity. And so playing with this mechanism, you can have gain as much as possible. Well, for different targets. In three-dimensional case, it's a little bit more tricky. So you don't have arbitrary gain, and we don't know yet what is the best situation we can have. So it's a little bit open. So, well, second problem, of course, well, it's all nice to look on the spheres or circles, but what about real medium? Of course, if you look on catalytic surface, it never looks like a sphere. So you have a porous medium, and you have diffusion-mediated reaction, surface-mediated diffusion in porous medium. Of course, as I said, the problem itself can be formulated, but there is no hope to get analytical solutions. So what can be done is numerical simulations, either by finite elements or by Monte Carlo or Brownian dynamics, so the different options to do. So, third question I already mentioned a little bit, so can one adjust absorption rate and the shape? So here one can think about some kind of chemical engineering, if it's possible to optimize the shape and the coating, so the parameter lambda, to get the best form. Well, I think the answer would be clear if we solve the previous one. Well, another question which is a little bit more formal, is the first passage time distribution important? Because as I said, it's possible to get, it's technically very heavy work. So, but the question is, do you need it? Because in many cases, in practical cases, the first passage time distribution can be approximated just by exponential distribution, in which case it's just enough to have mean first passage time. But are there some general conditions which ensure this property, I don't know. And finally, maybe the most mathematical question, well, what is the asymptotic behavior at large lambda? Because as I said, it's not easy to get the results. Well, we obtained them for some cases, but not in general. So I'm done here, and before you start asking questions, so let me ask you a question. And in fact, well, what I presented, it's just one of the topics I'm working on, and I have other projects, in particular on the intracellular transport. There is a poster by Jan, a PhD student, where we propose testing non-ergodic properties from single trajectories, and there are other stuff. So, and for quite a long time, I'm wondering, would it be possible to organize a long-term program on intracellular transport? Because I think it's really the subject which during the last 5 years, it's exploded. There are so many results, and it's really interdisciplinary topic. So you have mathematics, physics, a lot of biology, a lot of experiments, chemistry. So I think it would be really nice to have some program like this program here, but more dedicated to different kinds of intracellular transport. So if somebody in the audience is interested to be co-organizer of such an event, or if you know that such event is already organized, that would be nice. Or if you think being involved in that, giving talks, so just come to see me and or send me email. Well, originally I thought about IPAM institution. I already organized 2 conferences there. It was great. It's at UCLA. But of course there is no particular restrictions. It can be done anywhere, in particular maybe here. So I think that's all, and thank you very much for your attention.
Thank you. So, questions? Yes.
Yeah, so if you take lambda to infinity, how would the results, how are they sensitive to A? So A, let me understand, your A, it was a sort of an overlap of the domains between the
Yes.
interior and the right. You need to have that overlap.
Well,
What you call a physical absorption layer is really is this overlap in the domains. One, you applied the boundary condition, and then one, you applied it as a bulk condition, A inside from the boundary. So it would seem to me that if lambda goes to infinity, if lambda is large, it doesn't stay on the surface. But then when you kick it off, A is small, and it goes right back on the surface.
Yeah.
So then you have this sort of a singular limit.
That's right. In fact, well,
The A is
yeah.
And if it is, then it seems like it would be, the molecular details would be important.
So to some extent, originally we thought that A and lambda, they play somehow similar roles. So you can either increase A, for instance, if you increase A and decrease lambda, you somehow get the same problem. So in particular, we expected that the bulk diffusion would be obtained in the double limit when lambda goes to infinity and A goes to 0. And again, this problem, it remains to some extent open, because first, we, even if you fix A, but take limit lambda goes to infinity, you have some reasonable results. So you get some limits, you describe some dynamics, which makes sense. I think that, so in that sense, you have a freedom to consider them separately. But if you really want to recover bulk diffusion, I think in that case you have to take the double limit, because in that case, because in bulk diffusion, what you would get, you approach the boundary. When you hit the boundary, you reflect it immediately back, but you reflect it also in an infinitesimal small distance to some extent. So in that sense, I think that if you want to reproduce exactly the results from the bulk diffusion, you have to take the double limit. And then, well, is it just technical parameter, or it's represented from a physical point of view? That's a kind of big discussion.
Yes.
I'm trying to improve my intuition in this intermittency case. So I want to ask this question. So if I think about conditioning the particle and not having exited and looking at that distribution, that can be rewritten as an eigenvalue problem very close to the kind you're studying for this. Have you thought about that? Do you have any understanding of, as you change from this monotone increasing to this dipping region, is that quasi-stationary distribution concentrated in the bulk, or does it tend to be on the surface?
Well, I do not have answer immediately because we didn't look on that. That's a good point. I would say that, well, I have to think about it. I don't want to give you kind of false answer immediately, so I have to think about it. Sorry.
Have you got any scaling relation for your formula? In the sense, if you take r and lambda that go to infinity with the same velocity, in such a way that the ratio is constant, you get some simplification in your formula. Can you do some more?
Not real. Well, in some sense, when you have a simple case like point like target, then of course you can do a lot of things because, well, the formulas are explicit, and then you can really treat this limit. The problem is that in that case, well, you get first this is how, for instance, we got this behavior divergence as the square root of lambda, considering this limit. Because again, so just to remind the formula. Slow. Sorry. Why it's so slow? Okay, we almost arrived.
Because, for example,
yeah. So here in that case you have an expression, explicit expressions, and so you can kind of, well, our formula here, and then you can play with a, and you can see that a is a small parameter, so you can, if you think about it as going to 0, well, it's still a bit tricky in sense that, well, you have n is an index, so you have to be careful, but you can make some analysis. In general case, it's more difficult, because in general case, what will be analyzed to analyze the asymptotic behavior of these series, but some results were obtained analytically. Well, let's say few results were obtained analytically in general case, but some get some. One can guess some behavior, and in that case, one can do some scaling like that. But again, this is why I put this asymptotic behavior lambda going to infinity as an open problem, because from my point of view, it's not sufficient. Solved satisfactorily.
Question, so if you put your target inside, so I'm thinking in your annulus that might be easier if it's centered on the circle. Do you have results, and do you have similar sort of regimes where you could have a benefit in this case of surface diffusion versus bulk?
Oh, well, that was, so for instance, well, in a very simple case, if you take an annulus and you like put a target just in the center, then you can write easily the solution, and that's classical. So in that case, well, you can try to compare what happens. When Olivier Benichou and Raphaël Bartolier, they also published another paper, which, well, I didn't mention here, when they looked on the problem, so when they searched for a very small target inside, and also quite interestingly, they showed that in that case the surface diffusion can still be efficient, even if the target is inside. So the mechanism is a little bit opposite, because they will say that normally if it's in the bulk, that it's natural to go from the bulk. But the motion along the surface, it can be beneficial even in that case.
That's an analytic.
Yes.
Yes, final question on you.
So if I remember correctly, the results from the 80s of diffusion over polymers, they stated that it's always beneficial. The spatially diffusion is always beneficial. Can you comment on this? Like how it's related to your case, or it's not related, maybe the space is too curved for polymer search?
Well, I would say that well, the different results we get. For instance, in our situation, so we have this ratio on the D2 D1. So as I mentioned, naturally, bulk diffusion is considered to be faster than surface diffusion by many reasons. In that case, it's just often possible that this condition, it would be always satisfied in experimental setup, and then this is why it was observed as efficient. Well, now if you think about, I think then it depends on the applications. But if you think about, again, trying to apply this concept to the cell, maybe not the same model because it's too simplistic, then the bulk diffusion, you have very crowded medium. So I'm not sure that in that case, if you can look, for instance, bulk diffusion and motion on the microtubules, that could be the reverse situation. The motion on the microtubules could be much faster than in the bulk. And here it can be interesting, for instance, if, well, to which extent the cell is on the border or it's really in one regime or in the other.
Oh, let's thank the speaker. Thank you. We will reconvene.